Hey everybody, got another lesson for you today. This is going to be on exponential equations. This is going to be our week 5 lesson. We're technically starting a new unit. We're not really doing radicals anymore. That was last week. We finished that one up. So we're going to move on to exponential equations here. And this is going to be kind of a fun one because we've seen functions before, we've seen equations before. We've even seen exponential equations, but now we're going to look at it in terms of a graph and a table and how those kind of play out, because it does look a little bit different here. So what we're going to start with is we're going to start with a standard linear equation just to remind ourselves what these look like. And then we're going to move ourselves into the exponential equations, and we're going to see those differences in between theirs. So this one here, just your standard linear equation table. And how do we know that it's linear? Because we're just looking at it, and if you investigate a little bit, you can see that it is going to be a linear equation. But let's take a look at y. If we look at it closely, in between each of these, if we look at how these are growing, remember we have x's, which are the inputs. So this is going to be our top, which is the inputs, and then our y's, which are the outputs. And if our inputs are going up by 1, and our outputs are always going up by the same constant amount, they're always adding the same constant amount, then that is going to be a linear equation. So let's look at this one. The top here is going up by 1, and the bottom is going up by 3. Okay, so this is plus 1 on the top, plus 3 on the bottom. So this is where we would find a linear equation. If you guys remember our slope, remember M stands for our slope, is the delta y over delta x. Remember delta, this triangle symbol here, this delta symbol means the change in y. So how much is the change in y? Well, the change in y is 3. And what is the change in x, or delta x? Well, that's 1. So 3 over 1, our slope is 3 over 1. We could figure out our equation. Remember, this is our linear equation here. Y equals mx plus b. Well, m is our slope. That's what we just found. And then plus b, that's just what, when x equals 0, what is y? Okay, that's always going to be what our y-intercept is. Whenever x is 0, then what is the y value? So we could get our equation here, and this is a linear equation. Okay, so a linear equation has certain things. One of those things we talk about here, or a linear function, you can look at it that way, is a constant rate of change. Constant. This is always going up by the same amount. It is always going up by 3. And it's always, the y is always changing by 3 when the x is going up by 1. If the x is going up by 2, then you could say that the y is going up by 6, and that's still a constant rate of change. Okay, it's an equivalent ratio there. So this is a constant rate of change. Whenever it is a constant rate of change, we get a linear function or a linear equation. Okay, so the difference, let's take a look now at the difference here between linear function and then an exponential function. So let's put some information in there, and go ahead and take some time to write that down. If you're taking notes there at home, pause the video if you need to. But let's take a look at this. Let's look at our y's, our inputs. Okay, and we'll see how these are changing. So this is -3 to -2. Well, that's going to be 1, a positive 1, right? -2 to -1 is 1, to 0 is 1, 1, 1, 1, 1, 1. We get how that's going. So the top is going up by 1. Okay, so we can look at it there. We could just start at the 0. We don't have to start over there. Okay, but then what is the bottom going up by? What are the y's changing as? So let's take a look at the top. We know it's going up by 1, and then the bottom. So from here to here, we could say that this goes up 3, okay? But the other way to look at it is that it's getting multiplied by 2. 3 times 2 is 6, okay? And the reason why we're thinking this times 2 is because if this goes up by 3, from 3 to 6, if it's adding 3, well, then what is the next one doing? 6 plus 3 should have been 9, right? Well, that's not 9. That's 12, okay? And then if we add 3 again, it should have been 12 plus 3 should have been 15 or something like that, or 9 plus 3 should have been 12, right? But if we look at it in terms of, well, this one is, if we multiply by 2, it works, and if we multiply by 2 again, yeah, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48. What we see there is that these are actually going up by a multiplier. Okay, so we can immediately see a difference right here. In this one, it was adding 3. It was just taking 3. 2 plus 3, 5 plus 3, 8 plus 3, 11 plus 3, 14 plus 3, 17 plus 3, so on and so forth. Over here, this one is multiplying. This is our major difference, okay? So an exponential function is going to be going up by a multiplier. Now, if you're saying, hey, it's always multiplying by the same amount, that's constant. Yes, but you're not thinking of it in that in the right way. Constant is this adding of the same amount each time. This would be a constant ratio. So it's a little bit different. We've got constant rate of change. It's always going up by 3. Constant. It is always changing by plus 3. This one here, the amount that it's actually going up is changing. So over here, we would say it's going up by 3, but then from here to here, it's going up by 6. And then from here to here, it's going up by 12. And then from here to here, it's going up by 24 and then 48. So if we look at it that way, then we can see that the amount that it's changing is changing. Okay, so the change is changing. All right, this is going to get us an exponential function. So this term constant ratio is the thing that we're going to need to be looking at, because over here, a constant rate of change, you guys remember when we saw rate of change, that was also related to our slope. Okay, our slope and our rate of change is identical. Okay, it's the same thing. And so over here, the constant ratio, that's what we're going to need for our equation, because yes, we can get an equation from our exponential function here. So let's figure out how we can do this. The constant ratio, well, what is a ratio? Think for a second. Ratio is always in a form of a fraction. And where do you think we would put that fraction, or what do you think that would look like? Or I should say, where would we get that fraction from is something to think about. Well, if we're looking at the ratios between the numbers here, this is going to get us a ratio here. So 48 over 24 times 2. 24, or divided by 2 if you want to think of it that way. 24 over 12 times 2. 12 over 6 times 2. So there is our constant ratio. So the amount that it's changing is always going up by a multiplier of 2 there. So that's our constant ratio. Okay. This right here, just a standard function. Okay. This is what we would be looking at. This function right here is coming from this. I know it's kind of confusing that it's over here. Let me see if I can draw a little line. We'll do that. We'll draw a line right here. So that way it's separated out and that kind of goes up that way. So this is our function that's going to be for here. So where did I get all of this? Why is it f of x? Where the 3 comes from is the 2. This thing over here, let's take a look at it. Okay, f of x, we have seen this before. This stands for the function of x. Okay, what we would do is if we wanted to find what is the function of 2, if we had this equation here, well, we would put f of 2, and then we would end up replacing our x. We'll talk more about that in a little bit. It's essentially interchangeable with this y. You could think of it in terms of that, but it is it's a better way of thinking about our functions here. So let's see, where do we get this information? Hopefully you're looking at the 3 and you may be thinking, well, is this some sort of y-intercept? Yeah, let's take a look here. Okay, it is the y-intercept. It's essentially, where is this going to cross? Just like a linear equation, all graphs have to cross the y, unless, of course, they have a undefined slope, but we've seen that in linear equations. These ones are exponential, and they're going to have some different properties here. So there's going to be a y-intercept right there, and then the constant ratio is right here. Well, that constant ratio is where we found this multiplier right here, okay? So that's right there. And then the x, notice the x is in what position here? Well, this is a superscript. This is above the line, right? If the middle was right here, superscript is here and subscript is down here. Well, this is a superscript number. This is an exponential number. Okay, so the x is actually an exponent. Okay, so this would be our x value. So what is the if we wanted to find the function of 2, well, we would put 2 right up in here and solve this out, and that would give us our answer. Okay, so let's take this, which came directly from here, and figure out what it looks like in general so that we can apply this to a different scenario here. Okay, if we give these variables as opposed to numbers, so if we give this one here a and this one a b, so our a stands for our y-intercept and our b would stand for the constant ratio. Okay, so now, you guys want that again? Pause. Take a look at that, write that down, make sure that you get those identified. Okay, so let's apply this to a new scenario here. Okay, let's look at just a regular equation. Okay, this is just a standard exponential equation. Something we need to remember. We've been algebra students for almost an entire school year here, so we need to remember certain things. Remember that if there is ever if we don't see a number in front of a variable, what number is actually there? Right? It is a 1. Remember, there is always a 1 in front of everything. Everything can be multiplied times 1, and it doesn't change it. Okay, so this right here, this 1, it's written here, but what if it wasn't written here? For instance, what if it looked like that? If it looked like that, then you might be thinking to yourself, well, if I go back and I look at the other equation, it said that y equals, or f of x equals a times b. Well, there's no a right here. This is the b because that's the one that's attached to the exponent. So where is the a? Well, let's not forget the a is actually there. Okay, it's just a times 1. So if you don't see it, it's a 1. Okay? All right. So first thing that we want to do here is let's make a table. Let's take this information we have, let's turn it into a table. So we're going to make a table from -3 up to +3. Why? Why -3 to +3? Well, I like to see both sides of the vertical axis. Okay, if we go to -3, we've got 3 spots to the left of the vertical axis. We go to +3 and 3 spots to the right. It may work out, it may not. This is just something that you need to experiment with. So in each of these questions, try it out. If you don't like the data that you're getting, well, then try some different numbers in your table. But this is always a good way to start. What is the important number that we want to include? Well, we do want to include that 0 because that's what's going to give us the y-intercept. Okay? If we plug in 0 into our equation, then we will get whatever the y-intercept is, and where would that be? Okay? So that's why we want to have that number there. So let's take a look here. We've got a table. We don't have the outputs yet. We haven't solved those. And notice that I've started drawing myself a graph over here. Okay. Before we put numbers on here, let's start getting some numbers this way. So if we do this, if we start solving this out, then let's figure it out. If we plug in a 0, because remember, these are the inputs, the 0 into the x. What is anything to the 0 power? Do not say 0 because, again, we're not multiplying it by 0. When it's to the 0 power, anything to the 0 power is 1. Refer back to our lesson when we were doing exponential or exponents and working with those. Okay, it was when we divided those in a fraction there that canceled out. So it was 0, ended up, you'll have to go back and look at it. So that becomes 1. So anything to the 0 power is 1. Well, 1 times 1 is 1. Okay? And then if we continue on, let's take a look at it. So I noticed that I got 1/2, 1/4, and 1/8. Well, if x is the first power, okay, so it'd be 1/2 to the first power. Anything to the first power is itself. So that would mean that this is 1/2. Okay, 1/2 to the first power is 1/2. Multiplied times 1, it is 1/2. So really in this equation here, notice all we really need to solve is this part because we're just going to multiply it by 1. This isn't going to change its value. Okay, so 1/2 to the first power is just 1/2. If it's 1/2 to the second power, okay, write that on your paper and solve that out. 1/2 to the second power, remember that becomes 1 to the second power over 2 to the second power. So that becomes 1/4, and that's why where we get it right here. In fact, let me back up so that you can see this right here, and we can start pointing it out. So this is 1/2 to the first power, 1 to the first over 2 to the first. 1/2 to the second power is 1 to the second over 2 to the second. So that's where we get the 1/4. So that's how we get the 3 as well. 1/2 to the third power is 1 to the third power over 2 to the third power. Well, 2 to the third power, 2 times 2 times 2 is 8. So that's where we get the 1/8. Okay. Now, if we wanted to go the other direction, it's a little bit more tricky. Okay. If we do 1/2 to the negative first power, this is where we need to remember back to the rules for negative powers. Okay, negative powers, it didn't turn it negative. Don't do that. That's always the common mistake. What it does is it flips it over. Okay, you basically take whatever was on the top and it goes to the bottom and it gets the power. Okay, so let's take a look at it here. Okay, so looking over here, 3 to the negative fourth power. This is just an example over here on the left. This is not related to this one. It's just a way to think of it. 3 to the negative fourth means we go 1 over 3 to the positive fourth. Okay, that's how we would solve that. So then do 3 to the fourth, and that becomes a fraction. Okay, so how does this work with when it's already a fraction? Okay, here's another example. 2 to the negative third comes 2 to the third. Okay, so if it's already a fraction, what does that mean? Okay, so let's take a look at that. This would be 1/2, or 1 over 1/2 to the second power. Ugh, what? That's just disgusting. Okay, well, let's take a look at how this actually works out. Okay, 1/2 over that. Well, solve what's on the bottom. 1/2 over 1 over 1/2. Well, if you do that in your calculator, what do you get? Or really, if you wanted to, instead of divided by a fraction, you multiply by the reciprocal. Remember, don't use your calculator, come on. 1 divided by 1/2 is the same thing as 1 times 2 over 1. So the answer is 2. Okay, so let's try it again. How does this work for the other one here? Okay, y equals 1/2 to the negative second power. Okay, so then now let's start solving it out here. You could do all of this work if you want to, or you could see that it's going to be this over here. How might that change? Some of you might be doing that. Well, let's write it out. 1 over 1/2 to the second power, which is 1/4. Notice though we already did 1/2 to the second power, didn't we? It's right there. So that could go to the bottom. You've already done part of it essentially. Okay, well, we multiply by the reciprocal. Don't divide by the fraction, multiply by the reciprocal. So 1 times 4 over 1 is 4. You're already seeing the pattern here. Denominator, denominator. So what do you think the next one's going to be? 8, of course. Okay, so now we have our table, okay? You guys will get quicker at this as you're doing it, so don't think that it's always going to take forever, okay? So we did that. Now let's start plotting our points here. When x is 0, remember x, this is the x-axis. When x is 0, that means when it's in the middle. What is the y? Well, it's 1, so that goes right there. Okay, the next one, when x is 1, it's 1/2. So that means you're going to be technical here. You got to get down in the middle, and you're going to have to go halfway there. And then when x is 2, y is 1/4, so it's half of that. And when x is 3, y is 1/8. If this kept going, do you think it would be exactly on the line? No, it's not going to. We talked about this before where I walk towards the wall and I always cut the distance in half. Anyway, this is never going to touch that bottom part there, okay? This would be 1/8 and then 1/16 and then 1/32, and it would so on and so on and so on and so on and so on. And, anyway, you get the idea. It's going to keep going, but it's never actually going to touch this. It's going to get infinitely close, but it will never actually touch it. Okay, so we've plotted those ones, and then if we plot the other ones going the other direction, right, when it's -1, it's +2. When it's -2, it's +4. -3 is +8. Okay, so on and so forth. Now, we're looking at this really cool line that, oops, I gave you too much info. You could have paused it, but it'll come right back, so don't worry about trying to pause it and get all fancy. I forgot to put a mark there. So this is our exponential graph, okay? This is our exponential graph. It's going to get forever close to this, but not actually touch it, and this one's going to do a similar thing there, and you'll figure out some more things as we explore these later. Okay, so this is our graph here. We could say that this one is a decreasing graph. Okay, we can clearly see that the trajectory is going down as we go from the left to the right. Is it going up or down? Well, this one is going down. As we go from the left to the right, it's going down. So you could say it's negative or it's decreasing. And there you go. And then it will forever get close to 0, but it will not touch it. And we'll get into that in a little bit. Okay, so let's look at another table here, and let's see what we can make from it. So if you have this table, what sort of information can you gather? Well, how much is it going up on each time here? So this one goes up by 2, by 2, by 2, by 2. That's something to note. Okay, don't forget that. It doesn't always have to go up by 1. Every example we've had, the x's are increasing by 1, but what about down here? Okay, so then this one, it goes up by 20, and then it goes up by how much? 60, and then it goes up by how much? Okay, so let's take a look here. Okay, think about it. These ones go up by 2, and these are getting multiplied by 3. 10 times 3, 30 times 3, 90 times 3, 270 times 3. So what is our constant ratio? Okay, hopefully you guys figured that out. Okay, it's 3, and so we get this. So take a look at this information. Y equals a b to the x. Remember, a is the y-intercept, and b is our constant ratio. Okay, what if we wanted to figure out what our constant ratio was? Because is this one really, let me back up because that might be kind of confusing to you guys. Sorry, I went a little bit too far for you. Our y-intercept is going to be the 10. Okay, but why did I put 30 there? Why didn't I just say, isn't my constant ratio 3? Well, it'd be kind of confusing if you just put that there. Let's see what works out. We're going to plug in some numbers. Remember, y and x, these are actually points. This is not just two random variables. These are a point in here. 0 and 10, 2 and 30, 4 and 90, 6 and 270. You see how that works? This is an x. This is a y. So we put the 30. We're just choosing this one. Why not? Okay. We put the 30 right here where the y is. Our y-intercept is 10, right, because that's where the 0 is. Okay, so our y-intercept is 10. And then we would put b. And then our x, well, if the y was 30, then our x was 2. So we're going to put a 2 up there. Okay? So now what we're doing is we're actually trying to find our constant ratio instead of looking at it just trying to say, oh, hey, well, that's 2. Clearly it's 2. We're all good. No, that's not the case. Or 3. Sorry, Mr. Reinhardt's crazy. So let's solve this out. Well, we want to get rid of our 10. We want to move it to the other side. We're trying to isolate the variable. So we divide both sides by 10. Cancels out, so we get 3 equals b squared. And then if 3 equals b squared, then we would square root it to get b by itself. And therefore we get square root of 3 equals b, or 1.73 roughly, right? So our constant ratio is actually going to be the square root of 3. You don't need to write the 1.73 as that. We go ahead and write the most mathematically accurate answer. So it's the square root of 3. Okay, so that would be our constant ratio. So for this table here, remember, it was not as simple as just saying, oh, our constant ratio is this multiplier down here, when that's what it looked like for the other ones. Okay, that's what it looked like. This was getting multiplied by 1/2 and 1/2. Oh, look at that, it worked out. Not in this one. So if it's going up by 2 as opposed to by 1, you need to be careful. Okay, you're going to need to do this. Pick one of the points. A point here was 2, 3. Would it have worked if we did 4 and 90? Yeah, of course it would have. And it would have worked if we did 6 and 270, or 8 and 810. But why not use a small one, right? We don't want to deal with some massive numbers, okay? But yes, it would have worked. So our equation for this table right here is this. Okay, that's the end of it. I know, sorry, 22 minutes long of a video, but it can be a doozy of one. So you guys need my help with it. Don't forget, office hours are posted on the website, and you can always email me with any questions. The phone number there that you can reach me at, you can call that up. Okay, use your friends. Okay, glad to help, happy to help you. If you need help, just reach out, and we'll take care of it. Okay, enjoy.